Okay, so the blog we are dissecting today is from Instagram, which was published in the year 2017. The blog is about an optimization these folks did, and it is about they dismissed Python garbage collection. And what happened was they got a performance benefit. It helped them get better performance, and it also helped them save cost. So it is really counterintuitive, and that's what makes it quite fun. So let's start diving deep into it. And you can see I have a bunch of links open because I took liberty of going through it first, build an understanding because it is quite in depth, and it just helped me understand what exactly they would have done. Obviously they have revealed quite a bit of details, but not everything. So I try to primarily connect the dots there, right? Okay, so what they say is, by dismissing the Python garbage collection, which reclaims memory. So what garbage collection does, it reclaims memory by collecting and freeing unused data. Instagram can run 10% more efficiently. Now this 10%, it looks, hey, it's just 10%, but it is a gigantic number at scale. Imagine if Instagram was running their service on, let's say, 1,000 machines. Saving 10%, which means save 100 machine cost, right? And obviously they're not going 1,000, but with respect to the number of vCores they are using, it's quite a huge number, right? Imagine you chopping down your infra cost of one of your main service by 10%. If let's say your monthly cost is, let's say, $10 million and you save 10% of it, it's pretty significant number, right? Okay, so and this is what actually got me hooked to the blog, because 10%, which seems less, but at scale it's pretty like in absolute numbers it's pretty high saving, right? So by disabling, we can reduce the memory footprint and improve the we can improve the CPU LLC cache hit ratio. If you're interested in knowing why, buckle up. And actually we do need to buckle up for this because it is a huge blog. Okay, so let's first understand how Instagram runs their service. So Instagram's web server runs on Django, monolith, right? Monolith everywhere. Python to quickly prototype, and Instagram still uses Django. Uh, they are not definitely monolith. They have still they still have an enormous semi-monolith stuff, and then they have a bunch of microservices to do a lot of other things, right? And they run Django in a multi-process mode with master process that forks itself to create dozens of worker processes. Now here what happens is, like, we need to dive a little deeper over here. Is Python is a single threaded language, right? So what happens is, at any given point in time, if you would want to run a Python interpreter, it will always be clubbed to one CPU of your machine. So no matter if you run it on a 2 CPU machine or a 10 CPU machine or a 100 CPU machine, your Python process will always be leveraging just one CPU at a time. That's it. Now that's a limitation, right? Which means if you would want to utilize your underlying hardware fully, although your hardware is capable of handling, let's say it has 16 cores, you can run 16 things in parallel. You are not able to do it because of limitation of language. So which is where frameworks like Django, actually it's not the Django that provides it. The thing is that here the master worker concept comes in. So it's a very standard deployment way of doing it. In case you folks are unaware, there is a tool called UWSGI, and what it does, it is a fantastic tool. I've been seeing it in production and using it like since my early days. Everyone who uses Django, or everyone who has basic Python Flask based setup or Python Django based setup, UWSGI is almost the default way to go. And what it does is, it basically forks out a master process, starts a master process, and that master process creates a ton of worker process. So when your request comes in, it is directed to this worker process. And now this worker process, they typically occupy one CPU each. And then that's what helps you leverage and utilize your entire underlying hardware. So that's the whole idea behind it. Okay. And it does it with pre-fork mode to leverage memory sharing between master and worker. So here there are multiple modes in which it runs. One of the mode is pre-fork mode, which allows you to share the memory between master and worker. So the core idea here is that when your worker starts up, either it copies everything that the master has and runs it, and here it's not the data, it's the API server. So here what we're talking about is the code and the objects, the in-memory objects that it creates. It either copies that and runs in complete isolation, or otherwise the memory is shared between the master and the worker, so that the worker does not need to copy everything when it boots up, and it gives it a much better speed. So that's what it is doing over here. In the pre-fork mode, it leverages memory sharing between master and the worker processes. Here there will be talking about a concept called copy on write in some time, right? So that would solidify the understanding over here. Like here, one very interesting thing that happens is folks who have used Django in production know this very well, that OM is real. OM is out of memory. So Django, typically what happens with Django, like when you deploy Django in production, a bunch of memory leaks happen. It's not the limitation of Django, but maybe some library that you are using or a lot of memory that it needs to consume and whatnot. So if it goes beyond a certain thing, you can run into OM issues, which is why, and this was one of, like, when I joined one of my example, like, let me name it. Basically, when I joined Practo in 2015, this was one of the first configuration that I saw. Although we were not using Django, we were using Flask. This was one of the first configuration that I saw, which was about that there was an explicit configuration that used to kill the process every few minutes, that used to restart the worker every few minutes, and on a certain memory utilization. I'm like, why are you doing this? But you know what happened is, this is something that everybody does it. Everybody, whoever's running Python in production, this seems to be a standard because there are lots of memory leaks, maybe in our code, maybe high memory usage, anything. And this is very, 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 very common. So here, I always like when I joined, I used to only hear that like they are doing this, the process automatically reboots after some time. Like, who monitors this? That's when when I went deeper into infra configuration, I figured out that it was the magic of UWSGI that was doing it. And which is where, if I show you that option, if you go to UWSGI options website, the actual UWSGI website, you can see an option. Extra zoom. Wait. Okay. You can see an option called RSS, which is recipe here. Reload on RSS. This is that configuration. So here what it does is, it reloads the worker if the RSS memory is higher than specified megabytes. So when you are configuring your startup script, when you're configuring that, hey, when my UWSGI, so you run a UWSGI and you say that, hey, load this Django app and start it, you can configure this setting called reload on RSS. What this setting does, it says that if the memory of this particular worker goes beyond these many megabytes, right? Now this memory is what? Resident set size. So basically resident set, it's like, basically think of it like your RAM, basically what you're consuming there. If it goes beyond a certain size, you restart the worker. And this is a very common way to not deal with memory leaks, to not fix them, right? So you basically defer them, that upon you hit a certain limit, you reboot it so that you do not exhaust all the memory of your underlying hardware, right? And this is what you can see it with background jobs. Whenever there is memory intensive work that you are doing, anything that you do, if you run it through UWSGI, and typically any WSGI based web workers, this is quite common, right? And this was very odd. And by the way, there are other options, just to basically put this to completion. There are other options which says on max request or something. Yeah, here it is. So you can reload the workers after specified amount of managed requests. So let's say you say that, hey, reload the worker after it has handled 1000 requests. As soon as one of the worker handles 1000 requests, it reboots that worker, or it reloads that worker, it restarts that worker, right? And this is a very nice way to, you know, not fix the memory leaks. In case, obviously not every memory leak is in your control, because you rely on libraries which might have memory leaks. So this is something that comes pretty handy in most of the production grade system, and Instagram seem to be using it. Okay, enough. Now let's go to the next part. The next part says is, let's understand how this memory is consumed. So what happened is, what Instagram started seeing was that there was a spike in memory usage, right? And they wanted to know that why their memory grew so fast after it was spawned by the master process. So basically, when a worker was boot up, why did it why did it uh, why did the memory that it consumed went this high, right? So one observation that they saw was that RSS memory starts with 250 MB. Its shared memory drops very quickly from 250 MB to 140 MB within a few seconds, right? We'll basically come to this number in some time, right? The number here are uninteresting because they change all the time, but the scale of shared memory dropping is very interesting. Now here the thing was, the shared memory here, the memory was shared between the master and the worker, and it dropped about 1/3 of total memory. Next, they wanted to understand why the shared memory becomes private memory per process at the beginning of the worker spawning. So here, let's dissect this statement. So what happens is, although we say that the memory is shared, but what if I have a master, I have a worker. Master has created some memory. It is using something. It has spun up this worker. The worker initially references to the objects that is occupied by this master, right? But so long as it is read, it is perfectly fine. But if this worker updates its variable, so obviously the variables are like the variables are not shared, right? A worker will have its own set of variables. When something is updated by the worker, at that time, what happens is copy on write. So it's not that, because these are two separate processes, they cannot share memory very easily, right? So which is where what happens is, whenever the worker is writing something to the memory, let's say an object is changed, a pointer is changed, an integer value is changed, anything in a struct, anything that is changed, what happens is it creates a copy of the object and then it makes the changes. So it does lazily using copy on write, right? So this is what is an optimization that a lot of OSs do it by default. So Linux kernel has a mechanism called copy on write that serves as an optimization for fork processes. And it's a very common thing. Almost it comes by default, right? A child process starts by sharing every memory page with its parent. A page is copied to child's memory space only when the page is written. The page is returned to, which means, let's say I have a global variable count. So long as my, like, the count global variable is with the master process, the worker process is referencing to it. If the worker process does count plus plus, worker process needs to get its own copy. So at that time, this variable will be copied. I'm going at a variable level, but it happens at a page level. So this variable will be copied and then updated. Right? So what they wanted to understand is, when their process boots up, why the memory usage goes really high. Because the memory is shared. If the memory is shared, why is the usage going high? Because that's what the thing is, right? And this is the question that they started with, right? Okay, so here, what is their theory? And it is just their theory, it is not confirmed. This is how they did their entire investigation and then fix, right? Okay, so then what they started doing was, they started diving deep. They said that in Python land, because of reference counting, things get interesting. Every time we read a Python object, the interpreter will increase its ref count, which is essentially a write to its underlying data structure. Let me explain. So if you go through C Python source code, I would highly recommend you to do it. There are a bunch of videos on my channel. If you want to explore it on your own, do it. But there are a bunch of things where I actually covered this part. You can find it on my channel. But every object in Python. Actually, basically, if you look at it carefully, Python is just a wrapper over C language. So basically, C Python is implemented in C. Every object that you define in Python has a C struct to it. For example, every object in Python looks something like this. So type def struct underscore object, and every type of object, let's say string, int, string, int, float, list, tuple, whatnot, they all have this head object in it. This head struct in it. This head struct contains a variable called ob underscore ref count. This ref count is actually the number of places where this same Python object is referenced. So for example, if you create a list object and you add this list object into 3 different lists, the ref count will be 3, actually 3 plus something, but think of it that it is referenced from 3 different places, right? This is ref count. Now what happens is ref count is what? The number of places which refers to this object, right? Now the problem is that if I am, imagine this, my master process has a variable count which has some value, let's say 200, right? This count variable. I spun up a worker process. This worker process is initially what? It is initially referring to the same page where this master, where this count variable is referenced, because it is copy on write, right? So initially they are referred over here. But once someone refers it, CPython internally does ob underscore ref cnt plus plus. So even your reference is a write for CPython. Memory page gets update. So copy on write kicks in. So the entire memory space of master, almost entire memory space of master gets copied over here. And that's why the memory usage shot up. And then it started going down. We'll talk about why it started going down. Right? Now and again, this was a theory. This was not what they knew was definitely happening. This was a theory that they thought that, hey, this might be the reason. Right? Okay. So you see how read became right and superb, right? Okay. So the question is, are we copy on writing immutable objects such as code objects? Again, this is actually such a great question to ask, that here what we are actually doing is reading, but our read is triggering a copy on write. So given, and that too, our object is immutable, we might not be changing that count variable at all, but it is still triggering a copy on write because we referred it, because our reference increased ob ref count. Ob ref count led to a write, so a page got copied, right? So here, what is their first attempt? Here they made 4 attempts. This is first of them. What they said is, if ref count is the problem, let's disable ref count on code objects. So here it's something very fascinating. So at Instagram, we do simple things first. Given that this was an experiment, we made some small but hacky changes to CPython interpreter. They literally changed the CPython code and verified the reference count number did not change on code object. Like, see, whatever I explained was a theory, right? And again, everyone thought it could be correct. But what they thought is, hey, let's check that if our theory is correct or not. Because even when I was explaining it, it seemed quite plausible that, hey, this would be the reason. But this is why I actually explained it very verbosely, because I want all of you to think about that our theory might not be correct. It's always better to change things in production and change things and see and let data be someone who is dictating what needs to be done next rather than our guesses. Right? So what they did is they verified that the reference count number did not change on code objects and then shipped the CPython to one of the 4 production servers. Basically what they did is, the objects that they were worried about, they checked on the reference count of it. Or by the way, how do you check it? You can just check it with sys.getRefCount. If you don't want to change the CPython source code, it offers you a very nice API, getRefCount, pass any object to it. It returns the number of places where this Python object is being referred from, right? So that's how you can do it. But if you want to peek into CPython source code and change it, they did that. They obviously did not reveal it, right? What they said is, the result was disappointing. because there was no change on the shared memory, which they were expecting. They thought this was happening, right? But it was disappointing that this was not the actual reason. When we tried to figure out why, we realized that we could not find any reliable metrics to prove our hack worked. Nor could we prove the connection between shared memory and copy of code objects. Apparently, something was missing here. Lesson learned: prove your theory before going for it. This is such a beautiful line. Prove your theory before going for it, because we typically take things for granted. We say that, hey, this is my intuition, I would go with this and just move along, right? But it's better. Like, they quickly hacked and tried to prove their theory that it was copy on write that was becoming a problem, right? So now they wanted to go deeper. Right? Why is this actually happening? So what they did is, after some googling on copy on write, we learned that copy on write is associated with page faults in the system. Each copy on write triggers a page fault in the process. So if copy on write was really the problem, then the number of page faults should be high. So how do you measure the page faults? Using performance tools. So they went with perf tools that come with Linux, allow recording of hardware and software system events, including page faults. So by the way, folks, the sister programmers knows this really well, but you should definitely check out the perf tool, which comes by default in every Linux, right? And it actually, this also mentions, it allows recording of hardware and software system events. One of the most critical being page fault. It basically checks for few more events. We'll talk about it later, right? So what they did is they went to a prod server, restarted the server, waited for it to fork as in fork a worker process, got the worker process ID, and then ran the following command: perf record, what do you want to record? Page faults on this process ID, right? To measure how many page faults were happening, right? Now what they got was this. Now here you can see the number of page faults, but the most critical thing over here is, let's go to it. So it samples 2k, like 2000 of events, page faults. Every count approximately 91,000 page faults happened, and it happened in the collect part. Look over here, collect.part.7. It is in py object gc new, in a dictionary new in list editor. So collect is what is part of gc, garbage collection, which is what gave them. Now this is data backed stuff. They did not just went with like raw intuition, right? They went with data over here. The results were different than our expectations. Rather than copying the code object, the top suspect is collect. So although that might be the reason, but the top suspect came out to be collect, which belongs to gc module and is called when a garbage collection is triggered. So that's how they deduced it, that hey, it's a garbage collection that is a problem. After reading how GC works in C Python, we have the following theory. Again, theory, not something which is validated. But now look at the beauty of how they deduced it. Right? So C Python's GC is triggered deterministically based on a threshold. The default threshold is very low, so it kicks in at very early stage. Very early stage as in very early stage of your worker booting up. Because remember the problem, that when the worker was spinning up, the memory utilization was going up and then coming down. So because the default threshold is low, it kicks in at very early stage. It maintains linked list of generation of object during GCs, and linked lists are shuffled because the linked list structure lives in the object itself, just like OB reference count. Shuffling these objects in linked list will cause page faults to be COW'd, copy on written, like basically copy on write, which is an unfortunate side effect. Now this is where your OS basics come in. So what happened? Your linked list object got shuffled because GC kicked in. Because when GC kicks in, it would go and figure out, hey, these are the objects that I need to clean up. These are the objects that I need to keep. Imagine a doubly linked list. Right? When, let's say, from the middle of the list, when they are removing some object, they would want to remove it from the linked list as well, the reference from the linked list as well. Then the pointer change would happen. Right? The objects would be shuffled, so from back to forth, like let's say they would want to give a second chance to an object, it would move to the head of the list and whatnot. So because of this, there was a lot of page faults that was happening. And because of page faults, COW kicked in. An unfortunate side effect. Here, they mentioned how it is done. So you can look up this code in C Python source code. Is underscore GC underscore head, which contains the next and the previous pointer, as I mentioned, doubly linked list, and they hold like worst case alignment and whatnot. Like go through it. Then attempt number 2. What they thought is, let's try disabling GC. If GC is the problem, let's disable it. Right? This is such an intuitive thing. Right? So what they did is, in Python, if you want to disable a GC, you do gc.disable. Right? Such a simple thing. Right? You do gc.disable at the bootstrap of the script. So the first line that you run, just run gc.disable. So we started the server again, but no luck. Hey, even after disabling GC, why is GC not getting disabled? Why are we still seeing the same number of page fault? Because when they debugged it with GDB, they found out apparently one of the third-party libraries, they use something called as MSG pack, message pack. It calls gc.enable to bring it back. It's code written in the third-party library that they were using. It's so weird, right? That a third-party library is explicitly triggering gc.enable. And like triggering GC as in triggering the start of GC. Like, hey, my GC is enabled for this process now, right? So do collect the stray objects whenever you want, right? And this is so important. Like, even though you are disabling it, but some third party is bringing it back. So next step is, let's patch the message pack. They think that, hey, patching the message pack is the last thing we would do, because now you think that, hey, if message pack is the problem, let's patch it. But they did not go on this way. Why? Because it leaves door for other libraries to do the same thing in the future without us noticing, because it's not a foolproof solution. What if some other library does this, right? So first we need to prove disabling GC actually helps. Such a brilliant thing. The answer again lives in gc module.c as an alternative to gc.disable. They did gc.set threshold to 0. Such a nice hack. So what they said is, what if I set my threshold to 0? So this is where they went to the source code and figured out that they can just set the threshold to 0, which is typically GC is, not triggered. Sorry, which basically means GC is disabled without calling disable again. So it's like GC is still enabled, but because threshold is 0, it means it would not wait for anything. It would just keep it as is. Really nice, right? That's why I love this blog, because they went into so much of detail and so much of things that are not under our control typically, but it's really fascinating. Right? Okay, with that, we successfully raised the shared memory of each worker process from 140 MB to 225 MB, and the total memory usage of the host dropped by 8 GB per machine. So they increased the worker process memory. So whenever each worker is booting up, they said that initial memory. So when you start up a worker, you can provide an initial memory to it. That, hey, this is how much of memory it should start with. And what they changed it from 140 MB to 225 MB. But even after increasing it, the overall memory usage of the host reduced by 8 GB per machine. This saved 25% of RAM for whole Django fleet, which is their main service. 25% of RAM, which is humongous. Imagine, like, most of your infra cost comes from your VMs, and your VMs in most cases are eating things up. Like this, you save 25% of RAM, which means you can spin up more workers if you want to, or if not, you can reduce the RAM of your machine and save money with that. Right? So with such big headroom, we are capable of running lot more processes or running with much higher RSS memory threshold. In effect, this improves the throughput of Django tier by more than 10%. This is what I was explaining in the beginning. 10% is a massive improvement. So imagine if your monthly bill of this Django fleet was $10 million. By improving it by 10%, you save $1 million. Humongous absolute saving. Right? Okay, now let's move to the third part. Attempt number 3. Still, the kind of details they've gone into, it's way more deep now. Okay. The next part is what? Completely shutting down GC takes chunks. Let's go detail. After we experimented with a bunch of settings, we decided to try it on a larger scale. Hey, obviously, let's push it to production. We saw a massive improvement. Let's push it to production. The feedback was pretty quick, and our continuous deployment broke because now when they pushed it to production, they pushed it to larger fleet. It broke. Why? Because restarting our web server became much slower with GC disabled. My God, who would have thought? Who would have thought disabling GC would lead to slower restarts? But restarts are important. Why restarts are important? Because now imagine you do not have your GC triggered. And if you do not restart, then you would definitely hit out of memory issues. Right? So which means your UWSGI would need to constantly restart the workers. So now if your restarts are becoming slower, which means your in-flight request will be affected. So that's a problem. So you cannot have this. This is not a feasible solution. So you need to go deeper into it and understand why is that happening. So usually restarts takes less than 10 seconds, but with GC disabled, it sometimes took more than 60 seconds. Imagine you triggered a reboot of a worker and you are just waiting for 60 seconds just to get it up. What would happen to an in-flight request? You would have to have bloated infrastructure so that other machines are able to handle it. That would not serve the purpose. So what do? It was very painful to reproduce this bug because it was not deterministic. After a lot of experiments, the real repro shows in atop. It's a command which shows you memory usage, memory CPU core level usage, whatnot. When this happened, the free memory on that host dropped to nearly zero. So when this happened is what when a worker was restarted. When a worker restarted, the free memory of that host dropped to zero. Free memory dropped to zero, which means memory spiked up. The memory utilization spiked up, right? And then it jumped back. Now, when it spiked up and it jumped back, what happened? It freed up all the cache memory because it jumped up, added up, and then freed back. So a lot of memory, what you cached, got lost. Then came a moment where all the code and data needed to be read from the disk. And because it was reading from the disk, it was very slow. And because memory spiked up and it came back down because GCs and all, what all kicked in, what all happened, we'll go into those details in 2 minutes. It read the code that it loaded in memory, the objects that it created in memory, whatever was cached. It had to load a lot of code from the disk. And imagine a monolith in Django written, so much of code objects being created. A lot of them had to be loaded from the disk during restart of the worker, UWSGI worker, right? Okay, now what is happening over here? So this rung a bell that Python would do a final GC, final garbage collection before interpreter shutdown, which would cause a huge jump in memory usage in a very short period of time. So when a web worker restarted, what happened? When a web worker restarts, it kills its existing Python interpreter and starts a new interpreter. So when this interpreter gets killed or it's shut down gracefully. When it shut down gracefully, it calls this GC one final time. That hey, when he says GC final time, it's not that whatever objects were allocated as part of this interpreter needs to be cleaned up. For example, the type objects, the default, like Python internally caches strings through string interning. So small strings are cached in Python. Integers from -5 to 256 are cached. So all of these objects are created when the Python interpreter boots up, and many of them are created like this. Small strings are cached, small like strings as in the literals are cached, and all. They are all cleaned up. So what is happening over here is Python is doing one final GC. You'd say, but GC, it is just cleaning things up now. Why would it lead to a huge memory jump? Because running GC in itself would be memory consuming. Why? Because it needs to create its own data structures, go through it, figure it out and whatnot. So that does this spike. And again, I wanted to prove it first and then figure out how to deal with it. So I commented out the call PyFinalize. So PyFinalize is the code, this PyFinalize, what it does, it undoes all initializations made by PyInitialize and subsequent use of Python C API functions, and destroys all sub-interpreters that were created and not yet destroyed since the last call to PyInitialize. Basically, what I explained, whatever your Python interpreter created, it is deleting it all. That's the whole thing, right? That's what it is trying to do. And this triggers a high memory usage, right? So what it did, they commented out PyFinalize in UWSGI's Python plugin, and the problem disappeared. Bingo. So this is definitely the reason, right? So, but apparently we could not just disable PyFinalize as it was. We had a bunch of important. Now imagine if you disable PyFinalize, if you remove PyFinalize, what would happen? If you remove PyFinalize, we had a bunch of important cleanups using @exit hooks that relied on it. So basically what happens is, you can create @exit hooks. You can pass in a function object, create an @exit hook, which means whenever there is a graceful termination of your process, the functions that you have defined in @exit will be invoked. For example, you want to terminate all of your database connections. That could be one. You want to flush all the logs to, let's say, Sentry if you are using. You want to do, let's say, whatever something was written on the disk, you may want to just put it into remote server like S3. Whatever you want to do, @exit, you are doing it. For example, you are buffering, you are batching something, and a signal came in to terminate your process. You may just want to submit this batch to remote machine. Let's say you are capturing analytics and you want to do batch write somewhere. You would do it. So we ended up doing it by adding a runtime flag to C Python that would disable GC completely. So basically, they had a bunch of @exit hooks that they had to call. Now, what do? We had a bunch of important cleanups using @exit hooks that relied on it. So that's why they cannot just disable PyFinalize. What we ended up doing is adding a runtime flag to C Python that would disable GC completely. So basically, there's a flag, there's a code. You can just change the C Python interpreter code and just disable GC completely. It basically does not exist. Basically, 3-5 macros are there. You just make it empty. Done. You are done with GC, right? When they finally rolled it out to a larger scale, we tried our entire fleet after this, but a continuous deployment broke again. However, this time it only broke on machines with old CPU models, some Sandy Bridge. I'm not sure what that is, right? Maybe some CPU type, and was even harder to reproduce. Lesson learned: always test the old clients models because they are often the easiest one to break, and that's true. Everybody agrees to that, right? Okay. Now, because our continuous deployment is fairly fast, is a fairly fast procedure to really catch what happened, I added a separate atop to our rollout command. We were able to catch the moment where cache memory goes really low and all of UWSGI process triggers a lot of min FLT, minor page faults. Right? Bit of OS detail, we can skip that because the interesting part comes right after this. Right? By perf profiling, we saw PyFinalize again. Here. Where did you go? PyFinalize. PyType modified, we see PyFinalize again. Here. By perf profiling, we saw PyFinalize again. Upon shutdown, other than the final GC, Python did a bunch of cleanup operations like destroying type objects, unloading modules, etc. This hurt the shared memory. That although they disabled the GC, Python still did a bunch of cleanup operations. Like whatever I explained, like the caching of string literals, the caching of small integers, type objects, function objects, and whatnot. This hurted them. So what? Final attempt number 4. This is really super interesting. Now you'll see the magic that after discussing so much, the overall changes are just 2-line changes. So attempt number 4. Why do we need to clean up at all? First question, right? Obviously, the process is going to die. We don't really care, right? So the process is going to die. Another process is going to come back and replace it. Why do we care that we have to clean up? Because it is their code, their business logic, their batching, the examples I gave you, that needs to run. and they have to call at exit. They have to do it as part of cleanup, which is perfectly fine. Right? But would they care about cleanup of Python runtime? Not really. So long as their things are getting cleaned up, their at exit registers are getting called, their cleanup functions are getting called, good enough. But do they care if Python's cleanup is not working? Who cares? No one does. Right? So what they did is something fascinating. They added this one line as their bootstrapping script. What they did is just added this one line. At exit dot register os dot underscore exit comma 0. Let's go into this. What happens? So boot up script, that bootstrapping script is what? This is the first 5, 6 lines. How many lines are there? 1, 2, 3, 4, 5, 6, 7. These 7 lines are the first 7 lines that they run. Right? When that process is getting spun up, this is the first 7 lines that they're running. What are these first 7 lines? These are comments they won't do. So they started with gc.disable, but it did not work. So they run this gc.threshold, this one line. This is the first line, right? gc.threshold 0, because we saw what they need to do. They cannot disable because third-party libraries enabled it. So that's why they set the threshold to 0. And the second line that they ran, like others are comments. That's why I called 7. But the other line that they run was this: at exit.register os._exit 0. Now what is this all about? So what happens with at exit? Let's say you added at exit register, you added at exit dot register, and you pass in function 1, function 2, function 3. Now when the process is gracefully terminated, function 3 is invoked first, then function 2, then function 1. Right? So it is always executed. The at exit registers are executed in reverse order. Right? So now, because these are the first 2 lines, like actually effectively 2 lines, this one line and this another line, these are the first 2 lines that you are running. After this, the normal code is running where other at exit registers would be defined. Let's say batching and analytics and search indexing and buffering and whatnot. Those are defined after this, which means that they would be executed like batching, analytics, whatever they're doing, and other at exit registers, and then this would be invoked because it is happening in reverse order. Now, what is this function called? os._exit 0. Let's look at it. Tick, tick, tick. Okay. os._exit 0. This is the function call that they are making in at exit register. Look what it's doing. It exits the process with status n without calling cleanup handlers, flushing stdio buffers, etc. So it literally kills the process immediately without calling any cleanup, anything. The standard way to exit is sys.exit, which we all do, but underscore exit is something that is, they are literally interfacing with OS and then just like killing it. So no cleanup, nothing would be invoked. This is such a beauty because, other cleanup will be after this, but now with this at exit.register os._exit, 0, they're not giving up Python because they're immediately killing the process. They're not even giving Python a chance to call cleanup on their end. They're immediately killing it. This is based on the fact that at exit functions run in the reverse order of registry. The at exit function finishes other cleanup and then calls os exit 0 to exit the current process in the last step. With this 2-line change, we finally finished rolling it out to our entire fleet. After carefully adjusting the memory threshold, we got a 10% global capacity win. And I told you it could be in $1 million easily. This is such like so much of stuff. We spent how much? Like 45 minutes. And the final number of lines of change is what? 2 lines of change. And it's such an amazing blog. I just loved it. I went through it like many years back, but I was just redoing it because I just recalled it. I'm like, hey, let me go through it again and just be amazed and amused by it again. Looking back, in reviewing this performance win, we had 2 questions. First, without garbage collection, obviously now the main questions would kick in. Now that you do not have garbage collections, you are not calling the Python cleanup functions. Obviously, cleanup on Python side, even if you don't call it, it does not matter because the process is going to be killed and another one is going to be spun up. So it's not a problem anymore, right? But what if, because you do not have a garbage collection, wasn't the Python memory going to blow up as all memory allocations would not be freed over? Yeah, it would blow up. But Fortunately, this was not true. Let's see why. The primary mechanism in Python to free objects is still reference count. When the object is dereferenced, Python runtime always checks if its reference count drops to 0. In such cases, the deallocator of the objects will be called. The main purpose of garbage collection is to break the reference cycles where reference count does not work. Sure, look at this code. Do while if diff. Let's skip that. It's looking horrible. But you are basically calling deallocation. You're doing decrement of reference. You are calling deallocation on that corresponding object over here. But the idea is the purpose of garbage collection is to break the dereference cycle. Is to break the reference cycles. The reference cycles, if any, where the reference count does not work. Right. So that's one. Second question is, where did the gain come from? So basically, what they are basically proposing is that it would not lead to a higher usage of memory. Although it would blow up, but it would not blow up significantly faster. And even if it blows up due to high allocation, beyond a certain point, you have your OOM that reconfigure or UWSGI. That would anyway trigger a restart of the worker. So not a problem. I'm still yet to dive deeper into this, but still it's good enough, right? We can just appreciate what they did, right? Break down the gains. The gain of disabling GC was twofold. They freed up about 8 GB of RAM for each server we used to create more worker process for memory bound server generation, or lower the worker respawn rate for CPU bound server generation, which is fantastic. It's humongous saving. CPU throughput also improved as CPU instructions per cycle increased by about 10%. Now, what does this mean? This means that the number of CPU instructions that you could do per cycles is about 10%. Like, because you're saving on a lot of other stuff, your CPU is free to do other stuff, because at 10 you are limited by your underlying hardware, right? So they saw a spike in CPU throughput. They saw a spike in they saw a decrease in memory utilization. So win-win, right? It's a major win, right? So with GC disabled, there was 2 to 3% of cache miss rate drop, which was main reason behind 10% of IPC improvement. I'm not system programmer, well, that's fine. CPU cache miss is expensive because it stalls CPU pipeline. Small improvements on CPU cache hit rate can improve IPC significantly. With less copy on write, more CPU cache lines with different virtual addresses, bit of OS, not a champ in it. But the idea is the beauty of this thing, like the kind of depth. Who wrote this? Chen Yang Wu is a software engineer, and Min Ni, I hope I'm pronouncing their name right, is an engineering manager at Instagram. Definitely in 27. Not sure if they are there now, but these are the folks who did this. Like superb digging, superb analysis. The way they are going it in depth, like you can see how special this company is, right? How deep someone needs to go to, get the max out of their system, right? And by the way, this is one of my most favorite. I'm yet to understand it fully, given the kind of system knowledge it demands. I'm not a system expert, but I still love going through the details, right? So this is the blog. I have linked it in the description down below. Do go through it whenever you find time. Pretty fascinating. Okay, superb. So yeah, that's all what I wanted to cover in this one. This was a pretty fascinating blog. I would highly recommend you to do it. I'm still yet to understand it fully after reading it 3 times. But if anyone knows it, just drop me a note. More than happy to brainstorm together. So yeah, thank you folks for tuning in. This is it for this one. I'll see you in the next one.